MPLS traffic engineering, we started this in the previous class, but it was not a planned one. So we have a planned traffic engineering today. We got a presentation to follow. MPLS TE, traffic engineering, is not only by MPLS, even without MPLS, we used to do traffic engineering with BGP. When you say outbound policy, inbound, what it is? It is traffic engineering. You remember in BGP, we used to use local preference to impact the outgoing traffic. And we used to use MED or prepend AS in order to impact the incoming traffic. So what I'm trying to show here is traffic engineering is a common term. But what we are doing now is traffic engineering over the MPLS network. So you are having MPLS path, not just one, you're having MPLS path many. So we want to utilize fully the resources, optimal utilization. We do not want any path to be idle. We want the maximum utilization so that you can reduce the cost. You see, if you don't use the available path properly, then you are wasting the money. The cost has been wasted. So in order to reduce the cost, you need traffic engineering. Not only that, you want to prioritize a particular application traffic, then you need traffic engineering. You want to send all those voice traffic via a dedicated path, you need traffic engineering. And you want to have a dynamic tunnel, you need traffic engineering. So if you have any of this requirement, you need to go with MPLS traffic engineering. Now let's see what this presentation teaches us about MPLS traffic engineering. So what is MPLS traffic engineering? How does it work? MPLS traffic engineering capabilities, benefits of using MPLS traffic engineering, components of traffic engineering such as class-based tunnel selection, tunnel-based admission control, and also why you should consider implementing traffic engineering. So this, let's see one by one. Now, as we already spoke, in order to have an optimized, fully utilizing all the resource, full utilization, optimized, we want to have a very good performance. We do not want to waste any of the resource, any of the path. We need traffic engineering because it allows to control the path over the network by creating tunnels, by setting up tunnels between the nodes, between source and destination. So traffic engineering creates a virtual topology. So it's a virtual topology. Your physical paths are not really considered. You want to go from A to B. You have path 1, path 2, path 3. This is physical topology. I don't care the physical topology. I need a topology that meets my constraint, my requirement. So I need a topology to be dynamically built whenever I need. And the communication needs to happen between A and B. So in simple, what I want to say here is, I don't care whether it goes via path 1 or path 2 or path 3. I just want my constraint to be met. For that, tunnels, dynamic tunnels, by using one of the path which has got that guaranteed bandwidth is going to be created for my communication between A and B, which is what we call it as virtual topology. So with this traffic engineering technology, engineers can ensure that their networks are running at peak performance. So meaning I was talking about full utilization of all the resources, peak performance, the maximum you can get out of your topology. And not only that, you can adjust the path of the traffic according to the changing condition. So if this path is a preferred path, option 1, if that fails, it takes option 2 path. Option 2. That is what here it means. According to the changing condition, automatically the path has been decided because it's not physical topology we are depending on. We are using a virtual topology. Traffic engineering also helps to improve the network reliability by allowing the engineer to set up redundant tunnels in case of link failure or in congestion. As they already spoke, if one path, which is considered as primary, if it is congested, if you don't have enough bandwidth that your application need, it's going to take another path, going to create another tunnel. Same thing if the link fails, it's going to do the same thing. But don't compare this to a routing protocol. Routing protocol also, when a link fails, it picks another path. I agree. But what I'm trying to say here is, you might have opted for a path, you might have elected for a path which is not even in the routing table. And if that path fails, it is going to take another tunnel, a redundant path. So it also allows the engineer to prioritize certain type of traffic, such as voice and video. As I told you, I want the voice and video to take a dedicated path. That path need not to be there in the routing table. The path is there available, but it is not a best path. If it is a best path, everyone uses. In that path, when I send voice and video, they get lost. They get tail dropped. So I want voice and video to take another path, even though it is a little bit more metric. It is okay for me because it is free, it is available, it's always free. Packets can move faster than the path with the low metric. So this is why we need traffic engineering. So by using traffic engineering, engineers can ensure that the networks are running effectively and reliable. So not only effectively, it is also reliable. Not only providing you optimum utilization of all the resource, it is also providing the reliability. All the time, if one path goes down, you still do not know that the path has gone down. The packets are still moving via another path because it's a virtual topology. Your applications are no more dependent on the physical topology. If you tie it to a physical topology, when that physical path goes down, there will be a break in communication. MPLS traffic engineering provides virtual topology. This is the word that you are learning today, which I have not used in my previous class. I use the word tunnels, but basically it's a virtual topology. MPLS traffic engineering technology has got many advantages for network engineers, including improved performance, better scalability, increased flexibility. I don't think there is a need for an explanation. With MPLS traffic engineering, network engineers can easily adjust their traffic flow in order to meet their challenging demand, accommodating new applications. Example, voice. Voice application needs some dedicated path. So I want to adjust the traffic flow accordingly. So then you need traffic engineering. In addition, traffic engineering can also help to reduce the cost associated with the bandwidth or overutilization. Yeah, if you don't use all available paths, then you will be using only one path, which is shown in the routing table. then you will be ending up paying more money for overutilization. Or sometime because you are doing overutilization, policing will come and drop the packets. So to have better quality of service experience, you need MPLS traffic engineering. What it is capable of, it's the same thing what you have seen in the previous pages. It is capable of dynamically adjusting and controlling the traffic flow because it's a virtual tunnel, virtual topology. It effectively selects a path, quickly changes if there is any change in the topology. It also reduces the congestion. How? Instead of everyone using the same path, now you are able to load balance and improve the performance. Traffic engineering allows network operator to make dynamic changes in the way traffic flows through the network. You know what this means, right? It can be used for a variety of tasks such as load balancing, congestion control, prioritization, etc. Any questions so far? Okay, so by utilizing the MPLS traffic engineering capabilities, organization can ensure that the networks are running optimally, effectively. This is going to help to reduce the costs associated with the delay, inefficient cost of traffic congestion, ineffective routing decisions. So we have a lot of solutions. MPLS traffic engineering is the best solution to reduce the delay, inefficient caused by traffic congestion, and routing decisions. The benefits, they're going to repeat the same story again. MPLS traffic enables the administrator to configure and control the path of the data packet across multi-protocol label switching. Okay, this is an important point. Over the MPLS, only T can work. This allows to prioritize certain traffic so that you can reduce latency, increase the bandwidth. By using traffic, your organization can create multiple tunnels. Yeah, not just one tunnel, I tell you, you can have multiple tunnels to ensure that the data is transmitted securely and effectively. All right, components of traffic engineering. One important thing is MPLS. The other important thing is to monitor the traffic flow and ensure the data is delivered effectively. All right, so we have class-based tunnel selection. So you can classify traffic like voice traffic. We'll take tunnel number 1. And you may have TCP traffic. It may take tunnel number 5. So class-based. All right. So that based on the class, you place the traffic inside the tunnel and you admit the traffic. So the traffic is controlled based on the classification. We also call it as admission control. Tunnel is selected based on the admission control. So why you should consider implementing traffic engineering? Better QRS, better load sharing. I can bypass the congested paths. I can have dynamic VPNs. I can have fast reroute. I can have redundant path, high availability, scalability, all this. All right, so now very important story begins. RSVP based traffic engineering. So far, I have not used the word RSVP in the previous pages today. Here only it starts. RSVP. When do I need RSVP traffic engineering? If you have some admission control, I just told you what is admission control. You have classified some traffic. Based on the classification, you want to admit them in different tunnels. Then you need RSVP TE. Okay, so you also have some tactical path selection. Strategic path selection. You have some strategies. Then you need a traffic engineering. And traffic protection, meaning you do not want at any time the packet to be lost, so you need RSVP. IP and MPLS, okay, it's a very important point. Without RSVP, simply using IP MPLS is destination-based routing. What is destination-based routing? Traffic is going from 1.1.1.1, it goes to 2.2.2.2. In the middle, you have PE router, and you got a lot of provider-only router. You see how the labels are going to be picked based on the destination, where you are going. I'm going to 2.2. Oh, you want to go to 2.2.2. Okay, this is the label. Take this label and go. Again, another label, swapping the label, PHP comes here. And then VPN label removed and then goes out. What I'm trying to show here is, based on the destination, you move the packet. But MPLS RSVP traffic engineering is source-based routing. Source-based routing. I was telling you this yesterday, but I did not use the word source-based. I told you if traffic is coming from this application, then I need 500 kilobits reservation. See, based on the source, you decide the path, not based on the destination. Not based on the destination. If traffic is a voice traffic, then I need this much bandwidth. So I see what is coming from the source. I can match with an application, or I can match with an IP address. Very important point, very important sentence that you should make when someone is asking, what is the difference between IP MPLS routing and MPLS traffic engineering using RSVP? The difference is MPLS traffic engineering using RSVP is source-based routing. IP MPLS is simply destination-based routing. Did you get this point? This is important point. You are in mute. Right. Now, so these are all the important things why I need to go traffic engineering. I want to have optimized resource. I want to have disjointness, meaning at any point of time, I want the communication to happen, whatever the failure happens in the path, congestion, regardless of all those things. A regularity mandate means I must guarantee always my customer 500 kbps, whatever it takes. That's regularity. I have to. So even if one path goes down, I should not say, customer, wait for 10 minutes. We are fixing on it. We are working on it. No, I should not say that. Regulatory mandate says 24/7. The customer should have 500 kbps. Whatever happens, they should not get dropped. Then I need traffic engineering. And then application performance. Some applications need some bandwidth reservation. Right. So RSVP traffic engineering, MPLS trafficking allows the source routing in a dynamic or explicit way. I repeat again, the tunnel in which the packet is going to be placed is determined based on the source. Now the tunnel can be a tunnel dynamically decided. The tunnel can decide the path. Tunnel can decide which path, physical path to use dynamically, or it can be an explicit way. I told you in the previous class while I was closing the session. You can also say path 1 option. Use the upper path. If upper path don't have enough bandwidth, or if upper path fails, then option 2. Just follow what the routing table has got. That is explicit way of traffic engineering. So MPLS traffic engineer allows the source routing in a dynamic or explicit way. So desired constraints are defined at the source. What is the constraint? 500 kbps is the constraint. What is the desired constraint? What do you expect the traffic engineering to guarantee? I'm expecting 500 kbps to be guaranteed. Now, where do you mention this thing? Not on every router in the path. No. No need to do on every router in the path. Just define it on the head end. As the traffic comes in, if the source matches, if the source is having a constraint of 500 kbps, the head end is going to probe. It is going to probe all the path. And whichever the path has got this bandwidth will be used by the tunnel. So it is the source routing. Traffic engineering using RSVP is source routing. From head end, the entire path calculated and signaled. I was telling you this one very clearly in the previous class. It is the head end which is going to probe, and it is the tail end which is going to signal saying among these three paths, this is better. So that path will get a new label, and that path new labels will be used for communication. Once the communication is done, the virtual topology will break. It's runtime establishment. Here is the picture which explains you what we saw. You see the fish. The fishes are the normal packets. Or fishes are the packets. Usually the packets take the route which is there in the routing table. Whatever the IGP protocol prefers as the best path based on metric shortest path, that is what going to be used. But with MPLS source based routing, it can even use the other path. You see, the bottom path is never used. Always the fish is taking this path. Actually, this is called as fish topology, not because of fish is not a packet. See, the shape of the topology itself is a fish. The fish tail, the fin, belly, and the fish mouth. Okay, so anyway, coming back to the story, you have all traffic going via the upper path always, because it's the shortest path. You see the number of routers, this path is less than the below path. The bottom path would never be used. So only if the top path fails, the convergence happens, then the bottom path will be used. Whereas traffic engineering with MPLS can provide you optimal traffic usage, like even when this is available, you can make use of this path because it is idle, no one is using. Even though the metric is little higher, this can take your data much earlier than this congested path. To achieve this, we need what? RSVP, traffic engineering. So RSVP depends on these four things. One, you need a link state routing protocol. That link state database, it is distributed, and RSVP will maintain a database, the link state database, copying from ISIS or OSPF. Secondly, using the database, it calculates the constrained shortest path first. And then using the RSVP TE, the signaling from the tail end to the head end all happens, and the virtual tunnel is created. Now, placing the traffic on the tunnel, you can also do static. It can be class-based. It can be class-based tunnel selection. It can be auto route. It can be policy-based routing, or it can be simply normal forwarding adjacency or pseudo wire. Tunnels, meaning path option. You say use option number 1, option path option 2, something like that. So 4 necessary steps to calculate the path. The sending traffic in the MPLS traffic area, which we just now saw. So the information is distributed. This can only be done by OSPF or ISIS. You need a link state topology database. So you cannot use anything other than OSPF or ISIS. See, we also have a link state BGP. What is link state BGP? It's an address family in BGP which can carry the link state information of OSPF over BGP. See, when you redistribute OSPF into BGP, you can make BGP to copy the link state information and distribute it to the BGP peers. Why do we need that? This is needed to get overall view of the topology. Listen, please. When we have multi-area in OSPF or multi-levels L1, L2 in ISIS, knowing the complete topology is not possible. Do you agree? Multi-area, multi-level, because some LSAs are not allowed to go to other area. So in order to get a complete picture of topology, if you'll be running BGP along with this OSPF, you can use that BGP to throw the topology information of one area to the other. So BGP will carry that information, see? Carry the topology information at the specific node from IIBGP to BGP by redistribution. So after that, you can take from BGP, it will go to another BGP node. Maybe it will go to route reflector. And from route reflector, it will go to other ABGP neighbor, or it can be sent to a controller. Some controller. Example, PCE. PCE is one of the controller used in service provider environment, in which you can see graphically the whole topology. So using the tool, you can now configure tunnels, which we will be discussing in our Saturday class. Now, so the PCE is a controller, is a GUI to which all the link state informations are sent. So that graphical user interface will have a very good visibility of the topology. Now that tool itself can prescribe you the best path. So second step is topology calculation. Topology can be calculated either in a distributed manner with a constraint based shortest path first, or a centralized NMS, network management service controller, which I said PCE. See, we are not going to focus on PCE or this NMS. That's not our goal in this training. We are learning MPLS traffic engineering using constraint-based CSPF, constraint-based shortest path first. Now, MPLS traffic engineering allows constraint-based routing. Constrained, what constraint? It can be bandwidth. It can be segment routing. I want this particular segment. Or it can be administrative group to which the traffic belong to, something like that. So mostly, we will use bandwidth as the constraint as an example as we move further. Traffic engineering database is carried with the help of link state routing protocol only. I repeat. When you enable traffic engineering, you will be using one of the link state routing protocol. Now, I told you RSVP copies the database, but how it moves, it is going to use that same link state routing protocol header, LSA type 9. Right, that will be used to carry the information for traffic engineering. Input from link state database can be carried to offline tools and calculate end-to-end label switch path. Offline tools such as PCE and end to end why it is written ERO? See, input from link state database can be carried to offline tool to calculate the what? Calculate this one. Calculate the constraint based shortest path. Means the path via which you're going to distribute the label.
ERO.
It's not a ERO. I think there's some. I'll see. There's something wrong here. Our calculation is done in the distributed manner by CSF. So do not focus on this one. We are not going to use any tools here. We are only going to focus on constraint-based shortest path first. OSPF and ISIs has got extended. I told you in OSPF, LSA type 9 is going to carry the database information for traffic engineering. We're using that extension, type length value, TLV, in ISIs. OSPF analysis has been extended to carry the additional link state attribute for better traffic engineering with MPLS. So we have a picture in the next page where additional link state information is shown. This information is not kept in LSDB, but they are kept in traffic engineering database. I told you LSDB is copied to TED traffic engineering database. A separate database is maintained for traffic engineering. So those informations that we are going to see in our next page is kept not in LSDB because the constraint is not focused on LSDB. It is only focused on TED. Here it is. Link attribute for MPLS traffic engineering database. Traffic engineering interface, address, neighbor address, physical bandwidth, maximum reserved bandwidth, unreserved bandwidth, traffic engineering metric, administrative group. All right, so this is what, you know what it is, interface address, you know what is neighbor address, you know what is physical bandwidth. Now, reservation bandwidth is the bandwidth that we allocate for RSVP to use. Whatever is left is the unreserved bandwidth. And TE metric is nothing but the constraint. Administrative group is how much preference. If you have multiple tunnels, which tunnel need to be prioritized first? When you have multiple tunnels, I'm talking about multiple traffic engineering tunnels. There also you have prioritization. MPLS traffic engineering fast reroute. Fast reroute is a local protection mechanism. The router reacts to the failure is a point of local repair, meaning as soon as a particular path goes down, immediately the traffic will be swapped to another path. Say, for example, this is the primary T label switch path, LSP, this color. But something went wrong here so that it can immediately swap it via the other path. Subsecondary recovery against the node or link failure. Scalable 1:n protection. Great protection granularity. Cost-effective alternative to one-to-one protection and protection topology independence. So depending on independent on the physical topology, you are able to have tunnel. That's what reroute. Reroute means if anything goes wrong on a particular link or a node, what need to be taken that we define. That's what called as fast reroute. We said here, if something goes wrong with this link or with this node or something, we have said here, take this path. So only when something goes wrong, it will take the alternate path. It's called fast reroute. I explained this in the previous class. So whenever failure happens, the traffic continues through the alternate path since the MPLS traffic engineering fast reroute in the data protection mechanism, and backup path can be used as soon as the failure is detected. So before the failure happens, your router knows what path to use if failure happens. So when failure happens, it need not to search for an alternate path. It immediately pushes through the backup path. I explained you this one in the previous class. So control plane still converges. If the control plane finds more optimal path than the traffic engineering fast reroute backup path, label switch path, then the new more optimal primary path is signaled in the make before break manner. So you have said take this alternate path, but there's some better path is coming. So it's going to signal saying there is some better path. But statically, if you're given some backup path, it will take that backup path. If you leave it dynamic, then it will take the more optimal path when failure occurs. So in short, fast rerouting is nothing but data plane protection mechanism. Data plane is nothing but the path taken. So if path fails, immediately another path is taken. So here is the example. When there is a break in this link, you can see a label to move the packet this direction is given 30. So packet moves like this, and then PHP happens, and then the tunnel VPN label is 20. Sorry, this is the original label to go this way, but because there is a link failure, another layer of MPLS with new label is added. Using the label, packet immediately goes this way. And the stop label is removed. Now label number 20 is left. This knows what is label number 20. So you can deliver it out. Let me repeat again. This router provides label number 20 so that this guy can use label number 20 to reach D. But when packet approached here, it found that there is a link failure. So there is another label 30 given, but the problem is you need label number 20 to say I want to go to D. This router understands D only when you say 20. So that 20 is kept safe. The 30 newly added layer is going to be used, and this does PHP after receiving the packet, and it goes with 20. This knows who is 20. 20 is D, it delivers there. That's what we call as fast reroute link protection. So it is pre-signaled next hop. Point of local repair. Swaps the topmost label and pushes back the label. Backup terminates on the merge point where the traffic rejoins the primary. It rejoins the primary label switch path. Restoration time expected under 50 millisecond. Right. So basically, it's the same story again. Is it the same picture? No. MPLS traffic engineering fast reroute node protection. Node failure is less common compared to link failure. Thus, many networks only enable link protection. Not node protection, because node failure is less. What we saw is link protection. Now, this is about node protection. Most of the failure in the link failure is a link failure in the network. Node failure is less compared to that. MPLS traffic engineering fast reroute can cover all failure scenarios. An IP fast reroute technology such as loop-free alternate requires high mesh topology to find the alternate path, which will be programmed in the data plane. If topology is a ring topology, then a loop-free alternate cannot even work. See, it's a ring topology. Loop-free alternate won't work. More about loop-free alternate, we will talk when we go to segment routing. It requires a tunnel to priority queue node. A remote loop-free alternate is another IP fast reroute technology which allows to create a tunnel from what is PLR? PLR, point of local repair. which allows to create tunnel from the point of local repair to the priority queue node. Maybe we'll have another picture. Here it is. MPLS traffic engineering fast reroute node protection. See, there is a node failure. That's the difference between the previous picture and this picture. The previous picture, we did not have any node here. We did not have any node. Here there is a node failure. So label number 20 is given by this, label number 30 is given by this. But for this router to know where to go, label number 30 is important. So you see here 30 is maintained till it reaches the other side. The local given B given label is 40, which is top of the stack. Requires pre-signaling next hop backup tunnel. Point of local repair swaps the next hop label, pushes the backup label, which is 30. Backup terminates on the merge point. This one, merge point, where the traffic rejoins the primary. Okay, this is also merge point. Rejoins the primary. Restoration time depends on the failure. So this is all good to know, but you will not be needing this depth. But good to know, we need to know how these things work. Which single line command you're going to give when you configure fast reroute. But we need to know how it works. That's why we are learning. Just one line command there. Okay. Right.